So thank you for the introduction. My name is Holm, and I work at a company in Denmark called Force Technology. And shortly, we are a research and technological organization, which means that we are independent and self-governing. We provide services to the international market. What I'm going to talk about today is testing in a hydrogen environment, and also talking about the fracture mechanics, or specifically for pipelines. And in our company, we have hydrogen services within the materials and welding, testing, fracture mechanics, flow and metrology, emissions, measurements, and on-site inspection. So the agenda is start with the background for why I'm here and what we are working with. I'm going to talk about the fracture mechanics testing in hydrogen, talking about the fatigue crack growth in hydrogen, and also what the standards are saying and how we apply it in the fracture mechanics assessment, and then finally with the conclusions. So the background is a couple of years ago, the hydrogen or the infrastructure in Denmark needed to be compliant for hydrogen service, and that means that we needed to install new pipelines, and also some of the old gas pipelines, some companies wanted to convert them for hydrogen service. At that time, the most reference standard, at least in the industry that we talk with, was the ASME B3112. And in these projects, we have been involved in the risk assessment, methodological counseling, testing and qualification of materials for hydrogen service, and that's permeation tests, fracture mechanics testing is what we has just started up. And then also do the fracture mechanics assessment to determine critical floor sizes, lifetime, inspection intervals, and all this. So back when we started with the involvement in the hydrogen industry, as we are an RTO that needs to deliver service to the industry, we decided that we needed some test facilities for testing in hydrogen. There are two ways of testing, or there are several ways, so two of them are, one of them is, the first one I'll talk about is the stress intensity threshold factor that can be tested with a constant displacement or constant load test. And the equipment we have has pressure, and it can be pressurized up to 500 bars, and the temperature is between -20 to 200 degrees Celsius. This test method is the qualification testing according to ASME B3112, which is the hydrogen pipeline standard in the ASME code. And the testing refers to the ASME boiler and pressure vessel code, division 3 KD10, which then refers to the test method in the ASTM E1681. One of the test methods in the ASTM E1681 is the bowl-loaded CT specimen to obtain the stress intensity threshold factor K1H. The test procedure, just described in short, is that a pre-crack, a fatigue pre-crack is conducted in an in-air environment. The specimen is thus inserted into a glove box, which is in an inert environment where there are strict requirements on the levels of oxygen and H2O. And the bowl is preloaded with a clip gauge to know what the crack mouth opening displacement is. The specimen, or the several specimens, are then inserted into the autoclave. The standard specifies, or the KD10 in the ASME 8 defines 1,000 hours for carbon steel. And one of the pros of this test method is that several test specimens can be tested at the same time. One of the alternative test methods that we have also been discussing and also recently is the slow rising displacement test using the J integral according to ASTM E1820 or the ISO 7539-9 for determining the crack initiation toughness. And when we are looking at these two different methods, as I said before, one of the pros for the compact bowl-loaded test specimens is that you can test several specimens at once. It's quite cheap compared to the slow rising displacement, as you can only test one test specimen at a time. It is the test method that is referenced in the ASME B3112 and all the way through the other standards. And one paragraph in the Division 3 KD10 says that the results may even be used if plane strain conditions are not present. But we'll come back to that. And that's as long as the test specimen is within 85%, at least 85% of the final thickness of the pipeline. The con says that, it's based on the linear elastic fractal mechanics, which requires plane strain conditions, which may be difficult to obtain in the relatively thin pipelines. And research has also shown that the K1H testing give non-conservative results compared to the hydrogen crack initiation toughness for lower strength pipeline steels. And yeah, that's the results may be used even if plane strain conditions are not present in the ASME boiler pressure vessel code. Comes as a little, I was surprised that it's allowed, considering that the boiler pressure vessel codes usually are conservative compared to other codes. Next, we have the fatigue crack growth rate testing in hydrogen, and it has been extensive test programs have shown that hydrogen has a significant effect on the fatigue crack growth rate compared to in-air testing. And the curves shown here are from a NIST project where X52 and X70 steels shows the large increase in fatigue crack growth rates at both 55 bars and 340 bars compared to tests in air. These curves has then been used in the standards, and now I've taken three curves from two standards, and the ASME curve is the red one shown over here. If you look into the ASME B3112 standard, the threshold value is not specifically designed in that curve, so it continues down this way, but practically it has not been an issue in the assessments that we have conducted. So, but another problem is the R ratio is for less than a half. So this might give some problems when you are assessing wells, or if the pressure fluctuations are less than half the operating pressure, because then the R ratio is above the 0.5, and this curve is actually not applicable. The IGEM TD1 has two curves, one curve for the R ratio less than 0.5, and the blue curve for an R ratio higher than 0.5. This standard has a threshold defined at 2 megapascal square root meters, and it has two curves, as mentioned before. In general, the crack growth rates are higher in the IGEM compared to the ASME code, at least for the delta case above 6.5 megapascal square root meters. So in our work with the pipeline industry, we have also conducted fracture mechanics assessments. And we have done this according to the British standard BS 7910, as this is one of the two standards that I know that are used the applied fracture mechanics, the other being the API 5L, API 579. And to do these assessments, we of course need the dimensions of the pipelines, including the weld orientation. And this weld orientation actually gives some complications in the case of a spiral welded pipe. We need to know the probability of detection for different types of sizes and floors. A valid hydrogen stress intensity threshold value or hydrogen crack initiation value shall be available. We need to know the pressure, the residual stresses, misalignment, and so on, fatigue operation loads, and the fatigue crack growth rates. And then we can determine the fatigue crack growth according to the failure assessment diagram. And when it reaches the curve, then we reach an unsafe or a critical crack size. Talking about the spiral welded pipe. In BS 7910, it's stated that if the angle is below 20 degrees from the principal plane, then you can use a projection of the weld floor to either of the two principal directions. If the angle is above 20 degrees, then shear stress may have an effect on the results. And then it recommends you go to Annex A, which shows how you can combine different fracture modes, fracture mode 1, 2, and 3. The problem is that the standard does not have any standard stress intensity factor solution for mode 2 fracture. So in that case, we need to look elsewhere, either with fine element analysis or look at some of the comprehensive stress intensity factor solutions that are available in the literature. For this pipe, spiral welded pipe, we are actually in the dialogue of starting a full-scale test that could be quite interesting to fabricate with some prefabricated floors in and just start to test it with a fluctuating load to see if, or test when it will actually go through the pipe. Conclusions. So first of all, the current standards are not without issues. I know that a lot of standards within the hydrogen industry is in development, so still waiting to see how they apply the fracture mechanics in the new standards that are coming. The hydrogen stress intensity threshold value K1H can be obtained, but research has shown that it may be non-conservative value compared to the crack initiation toughness. And as I mentioned earlier, the boiler pressure vessel code allows for the K1H even if plane strain conditions are not present. Yeah, there's a difference between the fatigue crack curves, and I would think the ASME code needs to implement something that goes for an R ratio above 0.5. And yeah, the BS 7910 does not have stress and factor solutions for the mode 2 fracture. However, there are methods for evaluating combinations of several fracture modes in the analysis. And that's what I have for today.
Thank you very much.